Is there any other session going on parallelly?
No, sir.
No. Okay. Okay. So yeah, what shall we do today? Like, do you guys have any doubts, or do I have to go back to week two contents?
So calculation of directional derivatives.
Okay, calculation of directional derivative. Noted. And
Sir, if we can go content wise, that
Yeah, sir. Just a basic rundown of everything, if possible.
Yes,
okay.
sir, please.
So I have few slides with me readily. I will not be going through all the contents. Week two starts with like sets, and it goes on till directional derivatives and direction of the steepest ascent. So if I start discussing each and every topic, I may not be able to cover. But instead, what I will do is what are the main things we require. Okay, so the main topics I have picked, and in that I have directional derivatives also. So let me start with my with our discussion, and if we want to pitch into some topic in detail, then we can decide later on. Will that be okay?
Yes, sir.
So, is my screen visible?
Yes, sir.
Yes. Uh, can you see this machine learning foundations revision week two? Yes, I hope everyone can see.
Yes, sir.
Yeah.
Yes.
Yes, sir.
Okay. So this is okay. This is the link for YouTube, which I have posted in chat. People who want to see it in YouTube, you can watch it there. Okay, so let me start. Let us start. Okay, let us start slowly, and meanwhile, the other people will also join. So in this today's session, I whatever I picked is this. These are the most important topics which we use in future also. Like when you finish MLF, when you reach MLT there, and in degree level courses also. So these are pretty much useful, and I don't mean that the other topics are not useful. They are also equally useful, but these are slightly more useful. So I will start with this. So I'm skipping lecture 2.1, like again sets, functions, and all. Is that okay? So is there any doubt in 2.1 lecture? You can ask now, or else we will start with continuity. Like it started from maybe I guess how do we define sets, and then metric spaces, open ball, closed ball, right? Then vector spaces, norms, orthogonal vectors. No.
yes, sir. So I think we can start from continuity.
Okay. Okay, then let's move ahead. Let's start with continuity. And yeah, as this continuity topic you might have seen in max 1 or max 2 earlier, but again let us revisit this continuity again, because you need to understand functions uh, clearly. And in on top of it, usually when we see the data and when we wanted to put that into a function, we usually put the data or fit the data in continuous functions. And if you are using this continuous function, you should know what is continuity means, continuity of a function means. So let us start with this. So continuity is connected to a function. So a function is said to be continuous at some point x is equals to a. So when I say function, so this is what I mean. So the representation of a function is like this. So f is a mapping from one set to another set, where the first set is called domain, and this domain value, whatever the elements present in the domain, will be mapped to another set which is called codomain. And this mapping is like for every element in the domain, it will only map to only one codomain element. So then that kind of mapping is called a function. So that is the base definition of a function. A function is just the mapping from one set to another, and from the first set, every element inside the first set will map to only one of the element in the second set. So first and second I refer to, domain is the first set and codomain is the second set. Okay, this is a function, and there are many examples of the functions. So few simple examples are f of x is equals to x, which is a straight line. So this is a function. Also I can define like f of x will be x when x greater than 0, minus x when x less than or equals to 0. So this is like mod x. So this is a piecewise defined function, and this is completely defined on whole R on R. So these are few examples of functions where that function is like, yeah. So that's about function. And within the functions, there is one property called continuity. So functions are classified into continuous functions and non-continuous functions. So how do we differentiate this? And how do we differentiate this? Like this. So a function f of x, first of all, we will check this continuity at each and every point. A function f of x is continuous at x is equals to a, or x is equals to some point. Here a means any point. So a belongs to, in our case, belongs to this r, this r. Okay, if f of a, so the function value, so this is called, this is function value at x is equals to a. So f of a is the function value at x is equals to a, and whatever you see in this, so that should be equal to limit x tends to a minus f of x. So there are lots of fancy notations here, and this means, in layman words, this means what is the value of the function when I am approaching to x is equals to a. For suppose this is a, and this is left side of a, and this is right side of a. Okay, on the number line. So this is x is equals to a, and let me take an fixed value. Let us say a is 10. So x is equals to 10. I wanted to, I am at x is equals to 10. Okay, so left side of a refers to this, right side of a is this. So when I say x is coming from, so this means x is coming from left side of a towards a. So that means x, so x starts from here, it slowly starts coming towards this a. Okay, so that is what it means. So x, like x, if if a is 10, so x might start from 9.5, 9.6, 9.7, 9.8, 9.9, 9.99, 95, 99, 9.999. So like this, it is approaching towards a. What happens to the function value? So that is what this is, limit x tends to a minus f of x means. What is the function value it takes when x approaches from left side of a? And similarly, x tends to a plus means x is approaching to a from the right hand side, positive side of a. So that means from here, x starts from here, it slowly starts approaching to the value a from the right hand side. So that is why this is called left hand limit, because it is approaching from left side towards a, and this is called right hand limit. So LHL, RHL. So basically, if you wanted to check any function is continuous at point x is equals to a, what you need to check is, you have to check the function value at x is equals to a, and that should be equal to the left hand limit, and that should be equal to the right hand limit. So if this is satisfying, we conclude, so if this is true, we conclude f of x is continuous at x is equals to a. So this is at one point, single point. And when do I say f of x is continuous? Right? So no, I don't want to talk about a single point. I just wanted to talk about the function on and whole. So that can be done by checking each and every point present in the domain. So it's like if your domain is set of reals, we have to check at each and every point, like at every point the function should be continuous. If the function is continuous at every point x is equals to a, this is the statement. If the function is continuous at every, so now it is every point, it's not fixed a, at every point a, at every point x, and that x belongs to domain, then f is continuous. Is it okay? Can you read my lines, or do I have to improve my?
Yes, sir. It's okay. Fine, sir.
Yes, sir.
Awesome.
It's okay, right? Okay, maybe I will decrease this. Now it will be fine. Okay, so this is how we can conclude any function is continuous or not. So how do I say it is not continuous now? So continuous, we can check and conclude whether it is continuous or not. Continuous. But when will the function be not continuous?
When left hand
Sir,
limit is not equal to right hand limit,
So if any of the case being true,
positive.
all the things, if anyone is contradict the fact.
Yes. So when I said every point, even though if you get at a single point where this is not being equal, so all this function value is not being equal to the left hand limit, or maybe function value not being equal to the right hand limit, maybe this left hand limit and right hand limit may be equal, but it is not equal to the function value. So even though if you get one particular point, see, if the function is continuous at every point and it failed at one point, then also we conclude that the whole function is not continuous. Okay, or we say the function is continuous except at this point. Okay, so like this. So not continuous functions are failing this particular property, failing to be continuous at every point. Okay, so I'm not writing that, but I hope you will get it. So one thing is continuous. So this continuity gives us that how the function is, like, is it continuous throughout the domain or not. So you will get it. So this is one
Sir.
property. Yeah.
Sir, for continuous, we are checking for any one point. Then how we can make a statement like this? This function will continuous at every point.
So yeah, see here you are checking for a, right? Just put a variable like x itself. See, if I wanted to check, so let me take an example and check. Okay. So yeah, whatever you said is okay. How do I check at every point?
Yes.
Right. So if there are infinite points, I can't sit and compute every point. Yeah. So let me take an example. So a function is defined. Okay. Okay, let's put x square and x. Okay, is this okay? F of x is equal to x square plus 2x. Instead
Yes,
of putting, see, I just took a is equals to 10. Okay, instead of taking that a is equal to 10, just put it like at a, at any a. Just check what is f of a. a square plus 2a, right?
Yes, sir.
This is any a. This works for any a. Like you can pick a as 10, 20, 30, 40, whatever you pick, f of a will be correspondingly be equal to a square plus 2a. Now you have to check limit x is approaching from left side. What happens to this function? So how do I check the limit?
No, sir, it's done a minus h.
Hmm?
A minus h to the whole square plus limit h tends to 0.
So
Yeah.
this I can write it as, I will bring a new variable which is h. I will tell you this h is like the distance from the point A to present point. Okay. So it's like if your x is here and if your A is here, this h acts as the distance between x and your fixed point A, and this h slowly start becoming 0. So if this becomes 0, that means this x is slowly approaching to A. Or you can see it in the other way around. If x is slowly approaching to A, this h will become 0, right? So how can you write, see, this x and h? So x minus a will be h, right? If a is bigger, then a minus x will be h, and I can write x as a minus h. So that is what I will do. Instead of x and a minus, I will write this as x minus a minus is tending to 0. Now x minus a, x minus a minus is tending to 0 is nothing but the difference between x and a minus, that is h, and in place of x I will just substitute f of a minus h. So from there this comes. Okay, it's not that formula pe jao direct. You should also understand how that came. So this is what it is. Both are equal actually. So the limit, when I say limit x tends to a minus f of x, and when I say limit h tends to 0 f of a minus h, both are same. So now you can see f of a minus h when h is tending to 0. What will this be? So you can substitute and check. F of a minus h will be a minus h. So limit h tends to 0, a minus h whole square plus 2 times a minus h, and limit h tends to 0, a square minus 2ah plus h square plus 2a minus 2h. Okay. So as h is tending to 0, this term will go to 0, this will go to 0, this will also go to 0, and it will remain that a square plus 2. So the final value will be a square plus 2a, which will be equal to f of a. And also you can check for the right hand limit. Okay. So if I check for the right hand limit, what happens is this is limit x tends to a plus f of x, which will be limit h tends to 0 f of a plus h.
Sir, can you explain once how the x tends to a negative fx is equal to that h tends to 0 a minus h? I mean,
See, when x is tending to a minus, that means the distance between that x and a minus is becoming 0, right?
sorry, come again.
So this x is tending to a. X tending to a means x is approaching towards a, right?
Yes, yes.
So when x starts approaching towards a, what will be the distance between x and a?
It will become 0 slowly.
0 slowly, right? So that distance is h. We call it as h. Now, if I say x is tending to a minus, or if I say h is tending to 0, both are equivalent, right? If x is tending to a, that means the distance between x and a is becoming 0,
Yes, yes, yes.
right? So that is what. So the distance is referred to as h, represented as h. So even though if I say x is tending to a minus, or if I say h is tending to 0, both are equivalent.
Okay,
And
okay, sir.
similarly, we just substitute. So what is x here? So x is, if the distance is a minus x, and we represent it as h, so x will be a minus h. Okay.
Okay, sir. Got it. Got it.
Okay.
Thanks.
So one question.
Hmm.
So now, if it is not continuous, that means this from the left we will get a different value as an answer. Okay, what that means actually? So that means every point on the function, if we come from left, it is going to give the same value.
Not every point. See, that is what, if you are unable to conclude something here by picking any x is equals to a. Okay. So
Okay.
here the function is defined on whole R, and the function value at any point is x square plus 2x.
Okay.
But if the function is something like piecewisely defined, so something, if I define like this, x when x is greater than 0, and 1 minus x when x is less than or equals to 0. If I say like this, so I cannot talk like at any x is equals to a, right?
Okay.
If I talk like at any x is equals to a, my f of a, you can't write it explicitly. So what will be your f of a? Will it be a or will it be 1 minus a? So you will break it down into parts, right? If you say if my a is greater than 0, then you will write f of a as a. Correct?
Yeah. Okay. So in that case, so when you come from the left, we are getting a different equation. Okay, not f of a. What that particular equation represents?
This f of x, huh?
Yeah. Instead of f of x. Okay. Now we are getting a square plus 2a as an answer when coming from the left. That is equal to f of a. If it is not a square plus 2a, the result we are getting something else. Okay, maybe a plus
What
2a.
that represents is
Yeah. What? Yeah.
there is a gap between the function at that particular point. So it says that if I am coming from left side, I am getting different value. If I am coming from the right side, I am getting different value. That means they are not converging to one single point. They are converging to two different points at the same place. So that implies there is a gap in the function.
Yeah, but at what point, sir? Because it is not everywhere, right? Gap won't be everywhere.
So that you will get to know from the function. So if you see here also, this function will break into pieces like x greater than 0, x less than 0, and x is equals to 0. Okay.
Okay.
So you will get, in the case of x greater than 0, it is continuous. So your left hand limit will be equal to the right hand limit will be equal to the function value, and you will conclude that when x is greater than 0, it is continuous. The same case you will conclude it for when x is less than 0 also. But when you come to x is equals to 0 case, there the left hand limit will not be equal to the right hand limit, and it fails the continuity at x is equals to 0 for this function. Okay.
Yeah.
So
Okay.
this mostly when the functions are piecewisely defined, okay, then there is like corollary. You can take this as a corollary. If the piecewise functions are continuous by itself, so when I say piecewise functions are continuous, I mean x is continuous and 1 minus x is continuous in these intervals. Okay. And we know few functions which are continuous functions, like linear functions are continuous, polynomials are continuous, exponential functions are continuous. So we know few functions which are continuous functions. So no need to check for them again and again. Okay. Are you getting that?
Yes, sir. Yes.
So by seeing
So
this,
only the breakpoint. If it is a piece by, only the breakpoint we check. Then
we
if
need to
the
check.
both of the conditions are either polynomial, then we don't need to check, right? Yeah.
So it's like no need to check for x greater than 0 case here. No need to check for x less than 0 case. The only point you need to worry about here is x is equal to 0. And you have to check for whether your left hand limit and right hand limit are equal at x is equal to 0 or not.
Okay. If not piecewise, which other functions are possible to have a break? other than polynomials? Polynomials, there is no break, right?
Polynomials, there will not be break. Yeah.
What kind of, because by seeing the function, can we get an intuition this is going to have a step or break?
We can see there will be log mod functions. Log modulus some x minus 3 into x minus 1. So these functions will have domain itself break. Domain will not be R for this. Okay.
Okay.
Oh, sorry, not the mod. This one. So without mod. So log x minus 3 into x minus 1. If you try to plot this particular graph in Desmos, so it will show you in some intervals only. So in some intervals, the function itself is not defined. So maybe you might see graph like this, something like this. Okay.
Okay. Yeah.
Not this. Take minus of this.
Sir, in that example, x greater than 0, 1 minus x. So in that, you said that only at x is 0, it's not continuous. So, but even at x less than 0 also, if we substitute 0, we are getting answer as 1, right? So, that is also not continuous, no? I mean,
No. So when x is less than 0, we mean all the x's are now not 0. All are negative values. You should check for negative values. Okay, when you take the negative values, so you can cross check. For example, if you just take x is equals to minus 1, at this point you wanted to verify whether it is continuous at x is equals to minus 1 or not. So what happens to the left hand limit when x is minus 1? So what is f of minus 1?
I think it's has to be 2.
Yeah, 1 minus of minus 1, it will be 2. And what will be limit x tends to minus 1 of minus f of x?
Oh no, I'm not sure, sir, about this.
Okay. So maybe I'll just take one more page. Okay, let's solve this not continuous function. So those who are in the session, just try to solve this. X greater than 0 and 1 minus x when x less than or equals to 0. Okay. So I said we have to split it into 3 parts. One is you check for all a less than 0, sorry, greater than 0. You check for all a less than 0 and you have to check at a is equals to 0. So when a is greater than 0, I know my function f of a is a for any a. For any a greater than 0, I know that f of a is a. Also, I can compute limit h tends to 0, f of a minus h will be a minus limit h tends to 0, a minus h, and this will go to 0 and this will be a. And similarly, the right hand limit also you can check a plus h. This will become a plus h because the function is f of x is equals to x when x is greater than 0. So f of a plus h will be a plus h and h will tend to 0 and it will be a. So f of a is a, left hand limit is a, right hand limit is also a. So I will imply this is continuous for x greater than 0. Now let us come to when f is x a is less than 0. That means I wanted to check.
Sir, even there, a less than 0 is also continuous, no?
Is also continuous. So that also we can check using this. So let's write it down. What will be f of a here? When a is less than 0, what will be f
1
of a?
minus e.
So just look at the function. So when x is less than 0, it becomes the function behaves like 1 minus x. So that will be 1 minus a. F of a is 1 minus a. Now you have to check limit h tends to 0, f of a minus h. What is f of a minus h?
1 minus a.
1 minus of a minus h. Correct?
Yes.
Instead of a minus f of a, instead of x, you have to substitute a minus h. So that's it. So it will be 1 minus a minus h, and it will be limit h tends to 0, 1 minus a plus h. And as h tends to 0, this term will go to 0, and this will be 1 minus a. Similarly, if I try to compute limit h tends to 0, f of a plus h, this will also be like limit h tends to 0, 1 minus of a plus h. Okay. Because my function here, my function behaves like 1 minus x. So if it is a plus h, it will be 1 minus a plus h. And if I simplify this, it will be like 1 minus a minus h. And this minus h also will go to 0. This will also give us 1 minus a. So this is 1 minus a, this is 1 minus a, and this is also 1 minus a. Here also I can conclude it is continuous for x less than 0. Now you have to check, and this checking only. I said you no need to waste time for these checkings, because we already know few functions which are continuous, like linear. Linear means straight lines. Straight lines, polynomials, exponential functions, logarithmic, like log x, and sin x, cos x. So trigonometric functions. So these are well-known continuous functions to us. Okay, so that is why when you restrict, if you see here, this is a linear function. F of a is a linear function. You don't need to do all these things. It will be continuous. Here also it is a linear function. Now the only case we have to solve is what happens when a is equal to 0. Now what is f of 0?
1 minus
1 minus 0, which is 1. Okay. Now limit h tends to 0, f of a minus h. Now you see this is 0 minus h. Okay, now a is 0, so it is 0 minus h. So that means we are finding the function value for negative reals. So it's like f of minus h. Minus h is a negative number. So when it is negative, if you can see, when it is negative, my function behaves like 1 minus x. Okay, so what happens for this? This is h tends to 0. This is f of minus h. So when I substitute, this will be 1 minus of 0 minus h. Correct?
Sir, why did we did this f of 0 minus h?
Why did we get this?
Yes, sir.
We
0 minus h, f of 0 minus h.
we are checking for the left hand limit at x is equals to 0, right? At a
Because
is
a is equal to 0, that's why.
because a is equals to 0, I just substituted 0.
Okay. Okay.
Yeah. So this is okay. Like f of 0 minus h will behave like 1 minus 0 minus h.
Yes,
Is
sir.
this okay? Yeah.
Yes.
Sir, a minus h means the right limit, right?
A minus h is left limit.
A plus h is right limit.
A plus h will be right limit. See, that is why I told you, if you are confusing, treat it like this. X is approaching from a minus and x is approaching from a plus. So a plus is from right hand side, a minus is from left hand side. Okay.
Sir, 1 minus x is a linear function. No?
1 minus x is a linear function, right?
And how it can be non-continuous, sir?
1 minus x is when x is less than 0, right?
Okay. So this consider, well, this
Ah,
condition is also to consider that x is less than 0, then it is not true.
So now I am trying to find whether this is continuous at x is equals to 0 or not. So for that I need left hand limit and right hand limit at 0, Okay. So I am computing the left hand limit now. The left hand limit will be f of 0 minus h. So just like a here I know what is a. A is 0. So I am just substituting, instead of a, I just substituted a minus a. I just substituted 0 and I just written 0 minus h. So I have to identify this thing. So f of 0 minus h is f of minus h. So what will be the value f of minus h? Will it be 1 minus of minus h, or it will take minus h? Which one it will take?
So
1 minus of minus h.
Yeah. Tell me. I just need just how this f of minus h will behave. Whether it will go to the first piece or whether it will come to the second piece.
Second piece, sir.
Second,
Second.
less than
second,
zero.
sir.
Second one.
Second one. So if it is coming into the second one, I have to take this as the function value. So that is
Yes.
what I did. Instead of f of minus h, I just substituted 1 minus of minus h. And now this, if I simplify, this is like 1 plus h, and as h is tending to 0, this will give me 1. Okay. Let me compute the right hand side also. Right hand side will be f of h tends to 0, f of 0 plus h. Now this is like f of h. Now tell me, will how will f of h behave? Will it behave like it will be equal to h, or it will be equal to 1 minus h?
It will
H.
equal to h. Yeah.
It will go into the first piece.
Yes. X greater than 0.
Yeah. So that means this will be limit h tends to 0. Instead of f of h, I will simply write h, and as h tends to 0, this will go to 0.
Yeah.
Okay. You can clearly observe this right hand limit is not equal to 1, which is the left hand limit or the function value at.
Yeah.
Therefore, this implies it is not continuous at x is equals to 0. Okay. If you see the graph also, graph for this, how will the graph look like? When x is greater than 0, it behaves like x. We all know x will be the line like this, right? So this is x, f of x is equals to x, and I have drawn only from 0 to infinite because my function is defined like that. When x is less than 0, it is 1 minus x, and 1 minus x, if you draw, it will be like this. And at x is equals to 0, you can see 2 points, but which one is the value? So you just have to see from the question itself. It says x is equal to 0 also. At x is equals to 0, it behaves like 1 minus x only, not as x. So that means for our visually differentiation, what we do is we just make this darker point just to emphasize that at x is equals to 0, it behaves like 1 minus x, not like x. So that is why we put open circle here and closed circle there. Okay, just to emphasize that at x is equals to 0, you can see 2 points, but out of those 2 points, this is the value that x takes at 0, not this. So that is why we represent it like this. So there will be open circle and there will be like this. So now you can clearly see there is a big jump at x is equals to 0. Okay. So that will tell us that it is not continuous at x is equals to 0.
Thank you, sir, for this elaborate explanation.
Okay. So now this is so from graph, if there is a break, you can directly conclude that it is not continuous at that particular point. And mathematically, we do this for checking. Okay. Okay.
So one doubt, sir.
Yeah.
If the domain is a bounded domain, the endpoints, is that continuous or not?
See, if I bound like this, the whole function is bounded like this, then we conclude that boundary points are continuous because we don't know the left side of this point and right side of this point. So we don't have function. The only limit we have is for this particular point, the only limit we have is the left hand limit. We no longer have the right hand limit. So that comes under a special cases where some larger calculus required, higher understanding of calculus required, but there are theorems proven at boundary points. Many mathematicians concluded that it is continuous. We treat them as continuous if the left hand limit itself is equal to the function value.
Okay, thank you, sir.
So
no need RHL, sir.
Yeah, so no need RHL. I mean, see, if I have function only defined like this, okay. So I have only said f of x is 1 minus x in the interval minus infinite to 0. Okay. So this is how I define. So that means f I define from minus infinite to 0 close to r. And I said this. And I wanted to see whether it is continuous at x is equals to 0 or not. So at this particular x is equals to 0, we will have function value, we will have left hand limit, but we don't have right hand limit because we don't know how the right side of 0, the function behaves to the right side of 0. We don't know that. It is not given here. So that is why we only check left hand limit and the function value. If they are equal, then we conclude that it is continuous, but we don't really ask at endpoints. Okay, so it's as I said, it's an higher calculus. It requires some theorems and you should go through that theorems, and there they will use very fancy corollaries, the lemmas, everything will be pulled in, and few mathematicians concluded that yeah, it is continuous. We can conclude that it is continuous, but we don't need as of now. Cool. We move.
Yes, sir.
So just like we have seen continuity for a function, there is one more property called differentiability. So differentiability refers to how smooth the function is at that particular point. So is the function the rate of change of the function value is like normal, or is there any sudden change in the rate? So that is what we are going to do in the. So is the rate of change is continuous or not? Again, the differentiability is nothing but the function value, the change of the function value when x changes, f of x changes, and we are interested to see how it is changing. So is the change continuous, or is there any sudden drop or sudden difference in the rate? So this is what differentiability refers to. So if I wanted to be very what can I say, very informal way of defining differentiability is this. So whether my rate of change is continuous or not, we are going to see. And how do we check that mathematically? A function f of x is differentiable. Again, we will check at each and every point and also we conclude if it is at every point it is differentiable, we say the function is differentiable. Okay, same, just like continuity, same goes with differentiability also, but the checking and the conditions are different. That's it. So what we do here is we check for a limit, which is, we are not going to check for the limit of the function. Okay, so as x is approaching to a from the left hand side or the right hand side, we are no longer worried about the function values, rather we are worried about the rate of change of the function value with respect to the rate of change of x. What that means, like it is like the rate of change is referred to as dy by dx. So the rate of change in, so df of x by dx. So d refers to very small difference. Okay, d means it's like 0.1 and 0.11. So that's the difference between 0.1. So you can write it like this also, d or del. Some say del, some refer to this as delta. Very small change, we call it as d. So for a small change, the rate of, for a small change of x, how my small change of f of x is. So for that we see this. So it's like as x is approaching to a minus, the rate of change in a function value is f of x minus f of a, right? So you see there is a function like this, this is x and this is a. Okay, as this x slowly moving towards a, what happens to this f of x and f of a? So the difference between f of x and a is the rate of x, and the difference between this f of x and f of a is the rate. Okay, so the rate of change of f of x with respect to the rate of change of x. So this is x minus a and this is f of x minus f of a. Okay, so that is why, that is what it is. So we are worried about the limit value. So the value when x is approaching from a minus, what is happening to this f of x minus f of a divided by x minus a? So how the rate is changing, we will see that, and we will also compare this with the right hand limit. So when, what if x is coming from the other side, so the right hand side, then how is the difference between the function values with respect to the difference in the x? How is that limit? So if these two limits are equal, then we conclude that at x is equals to a, the function is differentiable, and we call we conclude that at x is equals to a, the graph is smooth, the function graph is smooth.
So it is like finding the slope when x limit x tends to a.
Yes, yes. So slope of the tangent line. Okay. So this, if these two are equal, we will represent it with one notation like this. So f dash of a is the notation for the different dx by dy by dx. So this is also called as df by dx at x is equals to a. So it's the derivative. So this is derivative. So the derivative value at x is equals to a is denoted as f dash of a. So this is, that's the denotation, and it is referred to as it will be equal to limit x tends to a. What happens to this f of x minus f of a divided by x minus a? So you see that is, numerator is the difference of the function values and denominator is the difference in x.
Excuse me, sir.
Hmm.
Sir, why are we interested in finding out the rate of change of x as it approaches a from both sides?
Because that will give you the smoothness of the function, right? Like whether the function is smooth, or if we are worried about, see, usually the functions are in real life, this will map to some feature to another feature, right? Like usually functions. So you see some, let's say that, let's go back to week one, that house. If you want to buy a house in some region, you will see for some factors, right? Like how is the locality, how many rooms that the house has, correct? So there are many features, and the distance. So the usual thing what we do is, let's fix with only one feature. We say we will be interested to see the rate of the house depending on the distance from the center of the city. Okay, so as you move far from the center, you expect the rate to get lower, right?
Yes, sir.
This
Yes,
is
sir.
the general expectation, and what we expect is the rate of change of the rate of the house as I move far from the center. We are very much interested to look for this, right? So we will look for this, right?
Yes, sir. Yeah, that would be one of the things we would look for.
So for, at those points, this rate is pretty much useful for a function. So derivative functions will act a major role. See, this is just one example I gave. Okay, every time we see functions, the derivative of that function also becomes a feature for you to analyze. Okay.
How much it is
Sir,
changing?
you started with continuity, then you're moving to differentiability. What way these two are connected?
How these two are connected is, see, if we are interested in rate of change from left hand side and the right hand side, first of all, the function at that particular point, it should be continuous at least. If it is not continuous, I'm pretty much sure that there will, the rate of change, or if I talk about the rate of change, it doesn't make sense at all. If both of them are pretty wide from each other, just like here, let's go back to this example. See, here it is not continuous at all. How can you expect the rate of change will be equal? It will definitely not be equal, right?
No, the rate of change will be probably equal and opposite.
Equivalent? Equal and opposite does, see, we are worried about sign also. Okay. Let me talk on this rate further in deep. Okay. So when I say, when we are saying that I am interested to see the rate of change of y with respect to x from left hand side and the right hand side, when will they be equal? When can be they be equal? Think about this for a minute or so. So when can this and this be equal? Okay, I will give you one more point to think.
If the curve is smooth.
It's a continuous curve without any bend or sharp corner.
Yeah. So if there is a break at that particular point, so if there is a break at x is equals to a, I can imply that these two values will not be equal at all. Okay. What I mean to say is, if x is not continuous at x is equals to a, the rate of change from the left hand side will definitely be not equal to the rate of change from the right hand side.
It may or may not be. So
No, it will definitely be not equal.
Continuity and the rate of change on both the sides of the graph, are they really connected?
Yes, of course, it's connected. See, you see the numerator, right?
Sir, if you see, suppose left hand side it comes on a parabolic and the right hand side it goes out as a straight line. So the rates are different. It goes as a straight line. Rates are different, but they are continuous, no?
Yeah, that can be there, but the opposite of that may not happen, will not happen. See here, it is not differentiable. The rate of change will be different here.
Yes.
Okay. It doesn't make you that the function is not continuous. But the vice versa of it is, if it is not continuous, then definitely the rate of change from left hand side and the right hand side will not be equal. So that I am concluding. So if you know that your graph is like this, okay, at x is equals to 0, I can directly, without computing this, I can directly conclude that the rate of change when x is approaching from left hand side and the rate of change when x is approaching from the right hand side will be not equal. We no need to compute. If it is not continuous, it will not be differentiable. Okay.
So like continuity, if at one point, if it is not differentiable, that whole function is, we say, not differentiable.
We say the function is differentiable except at this point. If it is like discrete points, it is not differentiable. We say like that. Or we can say that the function is not differentiable because it is not differentiable at this point. Okay. We say function is differentiable only if at every point this particular equation holds true. Okay.
So can you take the example of mod x and explain using this
Okay,
what we
mod
see on
x
the
is
screen?
very used function, right? Like
Yeah.
let's take okay, I will take a
Sir,
function.
can we take example of floor function? It would
Floor
also give
I
an
will, okay,
example of
maybe I will
continuous
take
between ranges.
so I will take an example and we will do. But understand differentiability. See, I am explaining this differentiability is more theoretical way because even though you have finished max 1, max 2, we guess that we see that many students are still facing problem in understanding differentiability continuity. So that is why I'm stressing more on this, because later on you see in later courses they will simply say it is continuous, and you see very like not even seen function you might have seen, and they simply call that function is continuous and it is differentiable at these points. It is not differentiable at these points. Until and unless you understand these terms very clearly, you will not enjoy the subjects. Maybe you will pass the subjects, but you will not enjoy doing it. Let me take an example.
So for the mod x, maybe you just mind to put it
No,
in
I
this
don't mind.
limits.
I will just put mod x if you want. Okay, so this is the mod x graph, right? Agreed?
Yes.
So this will be x when x is greater than 0, and it will be minus x when x is less than 0, and it is 0 at x is equals to 0. Okay, so this is mod x, and you can see this is continuous function. There are no breaks at all. This is continuous, and it is also differentiable at every point except at x is equals to 0. At x is equals to 0, if you see the rate of change,
0.
We will just compute it. Limit x tends to a minus, so I'm coming from 0 minus. So I will not use a, rather I will use 0, because we are worried about one particular point 0, or else let me put it as a minus 1. Now I am worried about f of x minus f of a divided by x minus a, right? So this I can write like this. Again the same thing. Instead of, even though if I say x is approaching to a minus, or if I say the difference between those two is coming closer and closer to 0, both are same. Agreed?
Yes, sir, got it.
So now, so this x minus a is h and x will be a minus h. So this is the substitution. So now as h is tending to 0, f of a minus h and f of a, and a is equal to 0 here. So if I substitute it, this will become limit h tends to 0, f of minus h minus f of 0 divided by h. So how will the function behave when x is minus h? Will it be x, will it be h, or will it be minus h?
Minus x. Minus x.
Minus x. Everyone?
Yes, sir.
Agreed? Yeah. So now this will be like limit h tends to 0. This will be minus h minus f of 0 is 0 divided by h. So if I simplify it, this will become minus 1. Okay. And this minus 1, if you cleanly observe, this is the slope of this line.
Sir, minus h won't be become minus of h?
Plus h.
Because it is approaching from left, so it will be minus x.
Will it be plus h?
Yes, sir.
No, that is why I will use a plus h here. Okay. See, it's like h is negative. Okay. H is negative and minus h.
It's fine, sir. It will be minus a minus h. We are testing from left hand side.
It will be minus h because we are coming from left hand side and it is even not.
Sir, it will be minus of minus h.
Yes, sir. Minus of minus h.
F of minus h.
Minus of minus.
Just hold on a second.
It is correct.
This is.
The rule came from x tends to a minus to h tends to 0. If we
sir,
come
we will
to
take
x tends to
minus
0
x.
minus, then it will be a plus x.
Yes, sir. Sir, it is minus x, right?
Minus
x. Yeah.
No, x is replaced with a minus h, no?
Sir, x is minus h, sir.
X is minus h, huh? X is a minus h. So x is minus
sir,
h.
A is 0, sir.
X is minus h.
No, x is a minus h.
X is a minus h, but a is 0, right?
So it will be minus h.
It will be minus h.
And we will put in minus x, I mean less than x.
When x is less than 0.
That definition.
Just 1 second.
So function is mod x, right? So minus h, it becomes h, right?
Sir, we'll park that one. We'll go for the positive side.
Positive side will become 1.
Yeah, we will work it out and compare it, no?
Yeah.
The negative h is taken care of.
No. It should be minus 1. Just we are confusing it minus plus.
Yeah, for that only can we do side by side?
Yeah. So this will be limit h tends to 0 a plus h minus 0 divided by h. Minus 0, I just took it like f of 0 is 0, and even a plus h is also f of h. And here I can see h is positive,
Yeah, then it's a +1, no?
See here.
So that minus h is taken care of.
Denominator should be minus h.
No.
No.
No, sir. In the previous limit, left.
The previous one, denominator should be minus h.
Yes, sir. Numerator will be plus h. Then you get minus 1.
Wait.
Yes,
X
sir,
is
because
equals to a
mod x
minus
is an
h.
even function, so values
Thanks.
inside
Correct.
the
Correct. So here it should be, see, I have replaced x with a minus h, okay? Then h will become a minus x. So just bring h on the left hand side, x on the right hand side. H will become a minus x. And denominator I have x minus a. So x minus a will be minus h. Got it?
Yes, sir.
Okay.
Then
So
it will become
denominator
minus
will
1.
become minus h.
Then minus h will become plus h.
The numerator will be plus h. Denominator is minus h. And it
That
will
is
be
f of a plus h, no? A minus of minus h, no?
a minus of minus h will become plus, or this, see, this function is a mod function, okay? Everything will be positive only. Whatever input you give, the output should be positive.
No, but the slopes are negative and positive, no?
Okay, let's compute this one. F of h is again h minus 0 divided by h.
That's one. No confusion there.
So this will become 1. So this is 1 and this will be minus 1. So the rate of
for that
change.
one only you said that you are going to put a of a minus of minus h and the denominator minus h. So the numerator plus h minus h is minus 1. Is that right?
The numerator is
plus h.
Yes, the numerator will be plus h, because that function we defined is a mod function, okay? It will not take negative values. So when I say f of minus h, the output should be positive value.
But you are not representing, the graph is representing mod function, but your expression is not showing any mod anywhere.
Okay. See, it will become minus of minus h, okay?
Yeah, that is what I'm telling.
Minus of minus h, and it will become plus h. And you can in the next line we are writing x as a plus h, okay?
Correct.
Right? Now h will become directly x minus a. So the denominator will become h in this particular case. But the denominator in the previous case, it will become minus h.
Right.
Okay. So the rate of changes are different. And also you see the rate of changes for this 1 and minus 1, they are actually the slopes of those lines. So minus 1 is slope of this function f. Slope. And if you see the slope of this is plus 1. Okay. And there is a sudden change in the rate. So that is why a sudden bend has occurred at x is equals to 0. So this sudden change in the graphs will tell us that the graph is not smooth at that particular point. If it is not smooth at that particular point, it is not differentiable. When I say smooth, if a function is smooth at a particular point, it will have a tangent line. You can draw a tangent line. Okay. And if it is not smooth, you might have more than one tangent lines can be possible, or you cannot even draw a tangent line at all. So there are many cases where if the function is not differentiable, you will not be able to draw a tangent line, unique tangent line at that particular point. But if it is differentiable at that particular point, then we can have a tangent, we will have a tangent line passing through that point and also touching the curve. Okay.
So this is not a differentiable, no? At x is equal to 0.
This is not differentiable because you see 1 is not equal to minus
1. But still we can draw a tangent line which passes through this horizon.
How? see the tangent lines, you will get like two tangent lines. One says like this, another says like, another will be like this. There is no unique tangent you can draw. So in this case, you will get two tangents.
Okay.
Thanks. Yeah. So that is differentiability. So understand differentiability in more theoretical manner rather than just by adding the formulas. Okay. So that is differentiability, that is continuity. And one connection between this differentiability and continuity is if it is continuous, if it is not continuous, you can directly imply that it is not differentiable. Okay.
Sir, could you scroll up to the previous page?
Yeah.
Sir, I'm a little bit confused as to why it's minus h in the denominator.
Okay. So that is how I defined, right? I took x as a minus h. Okay. Okay.
Sir,
As I said,
the setup was that in the number line, a was in the middle, and on the left side was x minus, and on the right side was x plus.
So see, this is x, this is a. When x is coming from left side, x is smaller than a.
Yes, sir.
Right? And the difference I said is h. Okay. So what is the difference between x and a?
H.
In terms of x and a. In terms of x and a, what's the difference?
A minus x.
A minus x. So that a minus x should be taken as h. So from this, how can I write x? What will be x in terms of a and h?
A minus h.
A minus h. When x is coming from left side of a. Okay. So when I say x is coming from left side of a, see this x coming from a, coming towards a from the left side, I should replace x with a minus h. So if I wanted to move to h, so that is why in place of x, I substituted a minus h. Okay. And
So
if you see the
function also we did the same thing, sir, in f also. F of x, we are putting a minus h. Simply.
In function only we put in place of x, I have substituted a minus h because I just wanted to remove x from the picture. So I just want everything in terms of a and h. So wherever x is there, I simply substitute a minus h. So here I substitute a minus h. Here also, when I substitute x is equals to a minus h, what will I get? A minus h minus a. So this is a minus h minus a. This will become a minus h minus a. This a and a will get cancelled, and in denominator it will remain minus h.
Okay, sir. Okay, sir.
Okay. So when x, you are coming from the right hand side, this is x. Now what if I say this is the difference h? Now what is the connection between a, x and h? How will the connection be?
H equals x minus a.
H equals x minus a. Now what will be x here now? A plus h. Understood?
Yes, sir.
So now in the next case, you just substitute in place of x, you just substitute a plus h. When you do that, your denominator will become h, and your numerator will numerator f of a plus h. You will have f of a plus h. Okay. Okay. So another contrapositive of this is if it is differentiable, then it implies that it is continuous. Okay. If it is differentiable, you can strongly believe that it is continuous. Also, if it is not continuous, you can strongly conclude that it is not differentiable. So these are two statements, equivalent statements more or less. So both are contrapositive to each other. So let me move forward.
Sir, if it is continuous, then it may be not differentiable.
May or may not be differentiable. The very good example is this. Mod x is continuous but not differentiable. Okay, so I will write those down also. So if it is continuous, it may not imply that it is differentiable. And again, contrapositive for this is, if it is not differentiable, you cannot conclude that it is not continuous. May or may not be.
That is the first point you have written, sir.
No, this is not differentiable does not imply not continuous.
That's what you are telling in the last point also, no?
First point is not continuous implies not differentiable.
It's ulta, not differentiable and not continuous.
Yeah. Okay, so this not, yes, no, it may confuse. Okay, that is why I said these are the two important ones. So what I say is by implies will not work. That's it. The below ones are by implies. The other way around things. They may be or may not work. We can't strongly say they imply that. Okay. Let's get into another topic, which is linear approximation. So linear approximation is very much widely used topic because linear approximations will give us, see, sometimes the functions you see nowadays, or maybe in these courses you might see only very good functions like polynomials, sines, nothing involved, there are no product of two different functions, simple, easy to understand, you can also draw the graphs and all. But in future or in your job, you will not see very smooth curves or very smooth, well-defined functions at all, where you can compute the values directly. At that particular point, understanding those functions will take like you may not be easily understand those functions. You just have to approximate that function to some simpler function we know and understand the behavior around that particular point. So that is what at max, that is what we can do.
Sir, is there any way to, understand or get hang of functions like tough functions, or is it through practice only?
No, it's like understanding difficult functions is still a problem to many mathematicians. It is very hard to understand it. See, that is what this continuity and differentiability will help, like understanding the graph function only. So how the function, whether I can, where the function is taking minimum value, where the function is taking maximum value, how the function is behaving throughout the domain. So understanding this for simpler functions is very easy. When it gets complicated, when you see the graph of some complicated functions, so understanding that graph itself will be difficult to understand. So that is why this linear approximation comes into handy. Okay.
Okay.
And most cases we worried. See, we are okay with errors, right? In these days, error minimization is there anyway, but we are okay to have some errors to leverage computations, right? That is it. There is always a trade-off between the approximation, how much error you can tolerate, and how much effort you can put it. You can, so for, if I have to explain in this mathematical terms only, so will you be interested to, if my function is simpler like sine x and I want the function value at x is equals to 0.0001. Okay, maybe not sine x is very easy, sine square x plus some cot x divided by square root of x square plus 1 plus log some function. Okay, so this is a complicated function you have and you want this particular value maybe at 0.1 itself. So how much effort you can put on this particular function and compute the value accurately, or if you are okay to have, if you are okay with slightly small error, you can, oh, you are okay with some 5% error you can have with the function value, and If you are okay with that, and if you can do it simpler way, then we are okay to take that. Okay.
Excuse me, sir.
Hmm.
So as you just said, real world functions could be very different.
Hmm.
So while solving a machine learning or data science problem,
Hmm.
is there a way that we can actually create an equation of the data given to us or the problems given to us, or
See, it's
it is
not
just
that
the
easy, right?
use of learning algorithm?
It's always learning algorithm only. It comes from there only. You cannot directly see. Definitely, data will not fit into any function. Okay, it's a myth. If someone says my data is accurately fitting into some function, some model, is actually will not work like that. Okay, so you can't directly get the function, or there is no algorithm predefined key. If I give you the data, it will directly fit. That is why there are loss functions we have. There will always be some loss.
Okay, sir.
Yeah. In real world, definitely not. That I can assure you. Maybe in problems which we give you might have zero loss, or it will accurately fit, but not in the real life. So there will always be a better model than the model you are using on the data. Okay, and we will try to find that better model. Yeah, see, most of the companies will invest money on this, getting the better models. They will always be worried about this cost minimization, right?
Got it, sir.
Okay, so let's talk about this linear approximation. So linear approximation, see, this is basically an approximation. Okay, so what we do is, instead of the function, whatever the function, we will try to approximate that particular function to a linear function or to a straight line. Okay, so and this is done at a particular point. Okay, so we cannot do like some random function is given to us like this, and you want linear approximation to the whole function itself. That will not work, and the error will be very huge. So you cannot get a linear approximation fit for this particular graph. Rather, you can always see, if I zoom this part a bit, it will be like this. If I zoom it, so this is how it is. And if you see, if you are worried about this particular point, okay, so you want to approximate, so and treat it like function is like this, something like this, and you want the function value at that particular point, and computational wise it is very difficult to compute, but you are okay that at this particular point, very closer point, there is one more point which is very closer to that particular point, and you know the function value at that particular point. So you know this particular point value, so you know this value, and now it is with us whether I can use this particular knowledge. So whatever the data I have, whether I can use this data and approximately find the function value at this point with some error, or am I not allowed to go to the approximation at all? And if you are not allowed, then we cannot use this linear approximation. But if you are allowed, and if you don't want to waste some time or energy of yours, what we can do is, whatever the data you have, so we have the value of this function at this particular point. So using that data, can we approximate the function value at this? So that is what this linear approximation is. So what we do is,
sir, may I ask a question?
Yeah.
One thing what I am not able to understand is, I'll take a very simple function x square. Now, when we are supposed to approximate the value of x square, right, at around around. So for example, approximate 2 raised to power 4. We can find it. Just taking an example, 2 raised to power 4 around 3. What does this means?
2 raised to the power around
2 raised to power 4 around 3. I mean, we have seen examples. There are examples in our practice assignment. E raised to power 0.0019 around 0 or around 1 or around 4. What does this physically will mean when we are saying around 1 or 2 or 3 or 4?
Okay, so they are so what they mean is I want e to the power some 0.001, but the function is behaving like e to the power x, and in order to get the value for this, I can treat it like there is a function f of x which behaves like e to the power x when x belongs to real. Okay, and I want this f of 0.01, right?
Yeah.
And when we say around x is equals to 0 means, f of x is if f of x is equal to e to the power x, what is f of 0? What will be f of 0?
1.
1.
E power 0. No,
E power 0. 1.
1.
So this value, and when we refer when we say around x is equal around 0 or something like that, means this. So we want you to identify some function that can be associated to this particular value, and considering that particular function, you just have to come up with a linear approximation function L of x at x is equals to 0. That is what we need.
So is this linear approximation we are doing to reduce only the computational time, or is there any other purpose?
See, for better understanding of the graph, you can say at that particular point. Okay, so as I said, whatever the graphs we have seen, we can actually analyze from the graphs itself. But as I am saying, there are many functions which you cannot analyze properly, very complicated functions which you cannot analyze.
But now what we are doing, that instead of one function, we will end up having infinite functions, right, at every point.
Not particularly. See, we will not have at every point. We will not be worried about at every point. Okay, so you will only be worried about if you are really worried about every point, then it's better to understand function itself rather than having infinite number of linear approximations. This linear approximation or maybe higher order approximations, what we are going to see later. See, this higher order approximation, the word approximation itself will tell you that we are approximating something, and in particular we are approximating functions. Okay,
but at what cost we are approximating? Do we have the losses?
Yeah, that is what. See, that depends on, again we will go to the cost optimization thing, cost optimization thing. So how much you are able to see, if you are okay with linear approximation will give definitely bigger loss. Okay, like the error will be large compared to some other better approximation, like maybe quadratic approximation is better than linear approximation for some functions. So that is what, how so if you are not okay with even for 1% of error, then you have to have some fourth order or fifth order approximation with you. So you should go with it.
So basically, sir, linear approximation, this smooth curve, we are making it as a faceted curve, right? With lines made up of lines. That is the graphical understanding, right?
Sir, this formula is actually, we have always been learning this. Can you like simplify the meaning of that?
Meaning of what?
This formula, which is boxed, no?
This one.
Yeah, I mean, we have always been learning this, but not really understanding the meaning, at least for me.
Okay, see, this is basically the tangent line equation at this particular point. So do you know how to compute tangent line for this line? Or else we can, it's very easy to understand also. See, we try to approximate, what we do is we try to approximate this particular function linearly. Okay, linearly, when I say, that should be a straight line, correct?
Yes, yes.
And also at that particular point there shouldn't be a error, right? Even if I say, see, if you see this particular line which I drew at this particular point, so even the value of this the value of the function at this particular point from this line or from this curve, both are same. At least they, at that particular point there will be no error.
Okay.
Right? And
Yes.
left to that or right to that, this straight line will have different value and this curve will have different value, function value, right?
Oh, yes, yes, yes.
So what we are doing is, here is, I am just approximating. So here I will just come back to my original graph. The graph is like this, but I don't want this bends or like steep things. What I want is, at this particular point I want a straight fit to this function. So if I want to have a straight fit, at least at this particular point the error should be 0. Okay. And from practice or from proofs which we define, see, there can be many straight lines passing through this line. There are infinite lines. Okay. And among these infinite lines, we concluded or we proven that whatever the tangent line to this curve is there, that is the best linear approximation we can have. That can be the best line to approximate. Okay, this is proven.
Okay.
So how do we find the approximation is good or bad? In this case, where we have in the peak the maximum point, the error may be more, but on the descent, on the sides, error will be less.
See, how do we decide good or bad is subjective. Okay, so it depends on comparing with some other line. Okay, so I conclude that this line is a better approximation compared to all other different lines which passes through that point. Okay, that we can prove, and it is proven. Okay, so if I sit on solving that proofs, it will take some time. Okay. But I don't want to get into that deep. How this is better?
No, my question, sir, is that, okay, when it comes to the highest point, the top peak point, so quadratic may be better, but when it's on the descending, linear and quadratic maybe not make much difference. So how do we decide that at what point which one we need to go? So it's difficult, right?
No.
Is it part of scope?
No. Always higher order approximations are better than the lower order approximations. Okay. So mostly higher order will give you better approximation. See, if I add some other value to this will give a better approximation. This will definitely take it closer to the function value only. It will not go out, it will not go away from the function. It will come closer and closer to the function only. So always higher order approximations are better approximations than linear, quadratic. So quadratic is better than linear. Polynomial functions of more than 3 degrees are better than quadratic, and like this, so on and so forth.
So why are we really struggling with this one when we already completed curve fitting and all those things which really maps exactly the real happening of the incident? No, when we have tools like that, why do we really need to go for an approximation, crude approximation?
That is why I'm saying, right? See, not always everything will be fit into curves. There also you are doing approximation only.
Yeah, we studied already curve fitting or trending or pattern matching or cluster finding and all those things we are doing. which is really mapping out to a real happening situation, close to comparing to the linear approximation what we are really struggling to learn what it is, because it's not really defined properly. There is a lot of loose ends.
No, I don't think so. See, without basic, see, whatever you said, clustering or everything,
We
modeling or
have
picking.
enough tools there, no, to really.
But yeah, see, that is what. So I have a favorite statement for this. I don't know how it goes, but see, you have enough tools in your car, right? Whenever a breakdown comes, will you call to a mechanic, or you will fix it directly?
I call the mechanic.
Call a mechanic, right?
Yeah.
So what if mechanic is not available?
Then I'll try to fix myself.
You will try to fix, and what if you don't know how to fix it?
That's it.
See,
That's it.
tools
Leave
are
the car.
it's like tools are readily available. Everything is readily available. We shouldn't worry about sitting here and studying. But see, when you code, or even in programming side also, when you're coding something, if some bug has occurred, you will not always go to your higher manager or someone to fix it, right? So everything is readily available, and you just have to copy paste it. Okay, you just have to copy paste the code and run it. And believe me, no code, like not code, few might work, but complicated codes will always give you bugs inside it. And you should fix it. You should fix it. Unless you don't know what is really happening in that copy pasted code, you cannot fix. That is what. So yeah, this is my favorite statement I used to tell to myself, as well as I used to tell for everyone. So understanding basic tools is necessary.
Right. How does it really
See, from here
challenges the
itself,
exam? That's what.
challenges the exam.
Yeah.
What do you
What type of problems are going to come with so far what we learned?
like? Same. Give a linear approximation to this function, or whether this function is continuous or not, whether this function is differentiable at this point or not.
And
Like
you're
this.
going to give a set of equations. You're going to ask me which is the best fit, something like that.
Which is the
best fit?
No, as I said, right? See, best fit is actually subjective. So if we
And
ask,
you said no. Someone has asked which is the best line, and you said there is nothing called best. It is all comparative.
yeah. So that is what I'm telling now too. So it's like best, good enough. All these are subjective to something else. We compare it with other, and we conclude that this is better. Okay. And as I said, right now all the models, so many real companies working on models, even they are better models. That's it. Always we strive for the best models to come up with.
Okay.
So if you want to come up with the best model, you should know from basics, right? You cannot directly build a model.
True.
If you have some 100 models with you, you can only conclude if you have models and what that model does. You can only sit with that 100 models, and you will conclude that this is better model. Out of this 100, this is better model. But it will be very challenging for you to come up with the 101st new model.
Okay.
Correct. So if you want to come up with a new model, then definitely you should understand from the basics. Within the model, what is happening, you should understand. Okay. So this linear approximation is the very base, simple approximation thing which we do. It's like more or less at one point you are fitting the curve. Basically, you are fitting the curve to the straight line. So the fitting starts here, and also at one point only, at this particular point only, we are trying to approximate that function using a straight line. So that is called a linear approximation. If I use a quadratic approximation, then that will be a quadratic approximation. So this linear approximation is the base to everything.
Okay.
And this linear approximation unknowingly we will do. We don't know the name linear approximation, but we do approximations in real life. Okay.
Sir, and how will the graph of third derivative, fourth derivative look like exactly? Like, how is there any change from the first derivative or?
Second derivative graphs, it depends on the function. No? See, derivative itself is a function again, derivative function.
Yes,
right?
yes.
When it is a function, it has some graph.
Okay.
Right? Double derivative is also a function.
Okay.
Okay. So for you to understand, if f of x is x square,
okay,
this is quadratic function, right?
Yes, yes.
The derivative of this function is 2x, which is a straight line.
Okay.
Okay. And double derivative of this is a constant function, which is 2.
Yes, yes, yes.
Okay. Like this. And all the higher derivatives will be 0 from like
Yes.
f triple dash of x is 0 functions. So from there it will be 0 for everything. Okay. So all these are functions and they do have graphs and everything.
Okay.
Again, you can study continuity, differentiability on derivative functions also. So that's a different topic. Okay. Yeah. So this is the key thing behind this linear approximation. See this linear approximation as you are trying to approximate some function at a particular point here, at some particular point. Why we are approximating? Because whatever the function we have at that particular point A, it is very easy to compute, but in and around that particular in and around A, it is very difficult to compute the values. As of now, treat it like this: compute the values or analyzing the function in and around will be difficult. For example, this thing only, e power 0.01. So now that you have calculators, you can use it. But think about some 700 or 800 years ago. What did they have done to compute e power 0.01?
Sir, I'm not able to understand the physical representation of this E.00. So we have a curve of E. When we will say e raised to power 0.001, it means x 0.001, we want to find the value, right? Then again, there would be something around. If you can just please draw a graph and explain that
Okay, we will
around
take this as the
specifically.
example and we will try to
Even x
analyze.
square would be fine to understand, not necessarily e raised to power.
Let me take e to the power x only, right?
Sure, sir. Fine.
So e to the power x, x belongs to R, and I know the graph for this. Okay, so how will the graph be? More or less. This is how it will be, e to the power x.
Yes, sir.
Right. So let me treat this point as some 0.01. Will that be okay?
Yes, sir.
Now, so I want this particular value. This is e power 0.01. Correct?
Yes.
The y value. So what we asked you is, we want an approximate value. So the question is like this: approximate value of e to the power 0.01. Okay.
So around, it says something else also.
See, see, around 0, we mean ki you will use linear approximation on the function e to the power x, and you find the linear approximation function L of x at x is equals to 0, and you just substitute 0.01 in the L of x. So that is what that means. But the crude meaning is, we want you to give us the approximate value of e to the power 0.01. So now, as I am asking you, if you don't have the calculator with you, okay, how will you find the value of e to the power 0.01? Any ideas?
Sir, we know e power 0. You have to approximate.
That is the only way. I just wanted to convince you, everyone, that only through approximation we can find the value e to the power 0.01, or else you just have to write down the value of e, which is 2.714 and so on, and you just have to take the power of it 0.01. So again, like it's like 100th root of 2.714, like this. Again, you have to be good at, as I said, you don't have the calculator to compute this also, so you have to good at how do you do the square root of 2, how do you do the cubed root of 2, just like that, how do you do the 100th root of 2.714. So you have to sit and solve it. You have to be like, you have to come up with 2.714, you have to come up with some x power 100, and you want that x value. We will write it into equations and we will try to go about. But that is very longest process, and then also I don't think you will reach the correct answer. So what we can do is we can approximate. So as this, if you see, e to the power, they are asking for e to the power 0.01, and this 0.01 is very much close to 0, right? 0 and 0.01 are very close to each other. When you compare it with minus infinite to plus infinite real line, this is pretty much close enough, right? Agreed? Yes, no, gave up?
Yes, sir.
So that is why what we do is we know the value e power 0, right, which is 1. So using this knowledge, using this particular, I will call it as data we have, right? Okay, let's, like, I know this e power 0 is 1, and I want, using this, can I approximate this? And answer for this is yes. So I can use e to the power 0 is equals to 1 to approximate the value e to the power 0.01. How is like this. So I know this value, just a second na? Okay, sorry for that. Okay, let's continue. So you know this value, you see the difference between these two is very close enough, very close. So it's like the value is somewhere around 1 plus something. So it is greater than 1, that's for sure, but you don't know what it is. For that, what we do is, at this particular point e to the x is equals to 0, what we will do is we will try to approximate this curve linearly. So that is, if I do it linearly, it is called linear approximation. If I do quadratic approximation, that is called, if I quadratic curve, if I wanted to bring into the picture, it is called quadratic approximation, like this. So I just wanted to come up with a curve which passes through this point. So it should pass through this point e to the power 0, because at least for the training data it should give 0 error, right? It should pass the training data. So at least for that, whatever the line I come up with, at least at x is equals to 0, it should give me 0 error. So that means my line which I am going to come up, as I am worried about linear approximation, that means I need a straight line that passes through this point and will be a better approximation to this curve around this. Okay, so passing through this point, there are infinite lines. So there is this line, this line, this line, and there will be one line, this line. So there will be infinite lines, and what mathematicians proved is if you wanted to do a linear approximation among all these lines which are passing through this point, x is whatever this point is 0, 1. So all the lines that pass through 0, 1, this particular red line which is tangent to this curve, this is f of x, and this is tangent to f of x. Okay, this line is a better approximation compared to the all other lines around this x is equals to 0. Okay, and we are interested to find this tangent line, and that we will say it as the linear approximation to this curve at point x is equals to 0. So let me compute that. So now getting something about this linear approximation? Yes, no?
Sir, could you repeat that point about the tangent? I think I missed it.
Point about the tangent. So among
the last
all,
point.
Okay, among all the lines which passes through 0, 1, so there will be infinite number of lines. Among all the lines, the tangent line, see this e to the power x is a smooth curve. It is differentiable at x is equals to 0, and there will be a tangent line at x is equals to 0. Okay, among all the lines possible, even tangent line will pass through 0, 1, and this tangent line is a better linear approximation to this function f of x compared to all other lines. So all blue lines are bad when it is compared to this red line. So this is bad. All these are bad approximations, bad linear approximation lines. Only this red line is a better approximation than all other blue lines.
Better because the slope is matching.
Better because you see the tangents, the left of the tangent and the right, it will be closer to the curve. They will be very closer, even though if you see the left hand side or the right hand side, compared to all other lines. It in that sense, the error will be slightly lesser.
Because the slope of the line is same as slope of the function at that point.
That because that is the properties of tangent lines. Those are the properties of tangent lines. Okay, I'm not going to get into that slope and everything, but instead what I want you to understand is this red line which I am showing. This is the better linear approximation to this blue curve line e to the power x at this point x is equals to 0. That from the graph also you can see. So this blue curve and this red curve around x is equals to 0. So in this interval, that red line is almost very close to that blue curve. Okay. So that is what the linear approximation line means. And how do we compute this linear approximation? So you know this point. Okay. So we need a straight line that passes through 0, 1, and the slope of this line is also slope of the tangent line is equal to f dash of x. Okay. So this is.
So if we try to understand the definition, the linear approximation, right? So it was like original value plus rate of change.
That you will get it now. So just hold for one more minute. We are going in that direction only.
Yeah. Okay.
Okay. So now I need this straight line that passes through 0, 1, and slope of the tangent line is f dash of 0. Okay. The slope of the function at that particular point is equal to the slope of the tangent line too. So that is what it is. So now I know the slope. I know one point. Can I compute the line equation?
Yeah.
like point slope form. So if I use that point slope form, y minus 1 is equal to f dash of 0 into x minus 0. This is what it is. And I simplify this. So just recall, this is point slope form. So if I know the slope and one point, I can write the equation of a straight line, which is y minus y1 is equals to slope m times x minus x1. Okay, this is x1, this is y1, this is m. So I just simply substituted it. So y from here I can simplify, y is equals to 1 plus f dash of 0 times x minus 0. So now I am writing this 1 as f of 0, okay, plus f dash of 0 x minus 0. So here I am approximating, I am finding the linear approximation at x is equal to 0. So this is a linear approximation. So L of x, sorry. So L of x at x is equals to 0. Okay. Instead, if I am interested to find the linear approximation at x is equals to a, so x is equals to 0 or x is equals to a, same thing, that linear approximation will be f of a, instead of 0 you just have to write a, f of a plus f dash of a times x minus a. So instead of 0 here also, if it is not 0, if you just treat it as x is equals to a, then also you will be like a comma f of a, right? So instead of 0 and 1s, you will have, so you will have your point will be a comma f of a, and the slope will be f dash of a. So again use the point slope form, you will end up getting the linear approximation. So you don't need to by heart this. If you know that the tangent line is the best linear approximation, you just have to find the equation of the tangent line. So if you find the equation of the tangent line, that will be the linear approximation. And for finding that straight line, what you have to do, you know the slope of the tangent line, you know the point also. Just by using point slope form, you can get this linear approximation. And this is what the formula also. L of x is f of a plus f dash of a times x minus a.
So sir, on the graph, E.001, E.01 at x equals to 4, what will be that point at x equals 4?
Around x is equals to 4, is it?
Yes, yes.
See, that
what will be that point?
That's very illogical to think, right? See, what you are trying to do is, you want this value, and what you are trying to do is, this is x is equals to 4.
Yes.
You
So
want to approximate. Huh?
That was a different question. That is about under root x tending to 3.9 at 4, like that.
No, that's fine.
No,
I
no.
wanted
He
to know
wanted,
this thing.
instead of x is equals to 0, see, if I do approximation around x is equals to 4, if I draw a tangent line and do the linear approximation, then you see, for that particular line, if I substitute 0.01, the error will be very high.
I see. Got it, sir. Sir,
Right?
यही जानना चाह रहा था मैं. Got it. Thank you.
Got it? Yeah. So that is why we should be betterly approximating the values, right?
I see. Thank you.
So that is about linear approximation, and linear approximation, please do not by heart anything. So this is my request, or whatever you can take. If you by heart things, you will definitely forget it one day.
Sir, how this f0 comes, sir, in place of 1?
In place of 1, because f of 0 is 1, right? See, f of x is e power x.
Oh,
F of
okay.
0 is e to the power 0 and it is
0
1.
is equal to 1. Yes, sir. Yes.
So I just came from that to this formula. From example, I just came to the formula. Rather, I should have gone from this to that. But for better understanding, I just took the example first and then compared it to the formula we have. Okay. Okay. So
Sir,
that
then
is
how do
about
we solve it for 0.01?
0.01. Okay. Now I have approximated that L of x is this. And what is f dash of 0? Okay. I have f of x is e power x. What will be f dash of x?
E power x.
E power x only. Now what will be f dash of 0?
1.
E to the power 0 and 1. Right? You know, now you see, I'll just remove this for sake. Now we are interested for L of 0.01. What is f of 0?
1.
1 plus f dash of 0?
It will be
1.
1.
Times x. Okay. So L of x. If you simplify L of x, we are going to get 1 plus x. Okay. Observe the function is e to the power x, and the linear approximation to that function, I got it as 1 plus x, which is a very straight line, and I can simply compute, or any, if I have given you any point, you can give me the value, function value, right? Now I want L of 0.01, because this f of 0.01, we are approximating it to L of 0.01, and this L of 0.01 is nothing but 1 plus 0.01. This will be 1.01. Okay, look how simple it is to compute e power 0.01. Getting it?
Yes, sir.
This is not accurate value. Okay, again, e to the power 0.01 is not equal to 1.01, but whatever the best sources we have, best resources we have, we used all the resources, and we are only asked us to give the linear approximation, not anymore. So the only best thing we can do is we can get this tangent line, and we can approximate that particular tangent line to the linear approximation and get the value as 1.01. And given to our resources, this is the best we can do to compute the value e to
Sir,
the,
how is it f of x is equal to 1 and f dash of x is equal to 1?
because
And
f of x,
linear approximation alone will be coming more than 1.01. How is that? It sounds a little bit out of it, no?
no, right? See, we are worried about, we know the function f of x is e to the power x, okay?
Yeah,
And if
yeah,
it
that's
is,
right. But what I'm telling, I'm just forgetting about the simplicity of the function. But the value-based judgment, it sounds a little bit wrong. It should be within, see, f of x is 1 and f dash of x is 1. So the value should be falling in somewhere in between. But why it is going outer bound?
why f of x is, see,
Because f of x is 1, no? F dash x is also 1.
f dash of 0 and f of 0 is 1, both are
Yeah.
1s.
Yeah. Sorry. So should it not be somewhere in between?
In between
The
of what?
linear approximation.
In between what?
Here it is both are 1. That's why. There should be less than 1. Is not it?
Why it should be less than 1? See, from the graph itself, you can see, right? E to the power 0 is 1, and e to
Yes.
the power anything greater than 0 should be greater than 1, right? E power x is an increasing function, right?
Right.
So if the e to the power something is increasing, the value should also increase, right?
But here e to the power what it is now we are finding it now.
E to
It
the power
should be
0.01, right?
0.011.
Which is
Okay.
greater than 0. So if it is greater than 0, I should get the function value to be greater than 1, because at 0 only it is 1 and the graph is moving upwards.
Okay.
So it will see this linear approximation moves to the closure side only. It will not go outside the, like it will not go to the negative side of the approximation. It will go closer and closer to the approximation. Okay, so that will go. So get better understanding on linear approximation. I will tell you linear approximation, not linear approximation, approximations we will definitely use in real life.
Okay.
So that is about linear approximations. These things we have done this. So now higher order approximations, it's just the extension of linear approximation. There will be one more term added to the linear approximation, which gives a better approximation. So this is better than.
So that is f double dash a by.
So this is a better approximation compared to this. So in lecture, professor has already taken an example and computed both the things, and we concluded, also professor has concluded or showed computing through quadratic approximation, it is giving us better result, better than linear. This is better than linear. Okay, and if I add one more, so this is cubic approximation. This will be better than quadratic and linear what we had. So if you slowly extend this to higher order, and this is nothing but the Taylor series of your function. So it will slowly, if you take higher and higher ordered values into the function, it will slowly be equal to the function. So it will actually moving towards the function values. Okay. So this is the Taylor approximation we know, right? F of a plus f dash of a x minus a plus and so on. So it will go to infinite. This f double dash of a by 2 factorial into x minus a whole square plus all these things, next things. So this is the Taylor approximation of any function. This is also an approximation, and this is the best approximation we have. So we call it as Taylor series also. So all the things are connected. Okay. So slowly this linear, quadratic and cubic approximations will slowly converge to Taylor approximation, and that Taylor approximation is the better approximation for the function.
So in the case of linear approximation, we have the tangent, which is supposed to estimate the point very closely. In the case of higher order derivatives like quadratic, what would we have? The tangent is a line, so it's linear. So for quadratic, what would
Quadratic
be?
is a quadratic.
So like a parabola.
It's parabola. It's a parabola equation, right? You will have x square term in u, x terms. So that's a parabola.
So parabola would come closest to the curve.
Yes, around that again.
Okay.
And higher orders, again, higher order will actually become closer and closer to the curve. Okay. So this is the higher order approximations. And then, okay, maybe in the next solidus, we can discuss more about directional. Okay, directional derivative, let me finish. Okay, directional derivative, just hold for some 10 more minutes. We will discuss this directional derivative. I'll just directly go to the direct formula I have.
So solvitus session will also taken by you only?
Taken by not me, but I will inform the instructor to discuss concepts also. See, how are the questions, by the way? Is it difficult compared to maths
Difficult, sir.
Compared to difficult?
You have to understand. If it is simple, straightforward math, then it's okay. But framing the problem is
Okay. Now you feel maths is much more simpler than MLF.
that's a good scale of pressure. Yes. Put on
Uh,
one more difficult subject, math will become easy.
yeah, maybe if you move to MLT, I will definitely, for sure, I can say you will feel MLF is the easiest course you have studied in diploma.
And I probably hear from everybody.
Sir, which is the most challenging in this data science thing?
PDSA.
Most challenging.
PDSA is the most challenging thing.
No. I'm saying
PDSA comes under programming, right?
in
Yeah.
data science.
So data science, I think you might feel little worried or depressed in during projects. You have to do it in MLP. So while doing that, many were failing in them. So if you are following some in Insta pages of IIT you will get to know.
So strongly recommending not to take both together. No, take the project separately.
So we recommend you do MLP first separately, and then take a project later on.
Sir, but in projects they do help, or it's we are on our own completely?
No. We do help, but it will not be like spoon feeding help. So we'll ask you to read some papers, or I'm not sure about it, but students actually, whoever students I have met, my old students, they were like, this MLP project is killing them.
So, sir,
So,
you all will be one of the instructor there?
No, not in MLP, definitely.
so this is the first time you are taking MLF course.
Yeah. So for the past 2 terms, I was there in MLF, but I haven't taken sessions because. So even at that time, also I'm in learning stage. Okay.
So it seems like God sent you for us.
No. See, everyone should learn. Like, even though we are instructors, we should learn and then teach, and understand and then teach. So it took me 2
Sir,
terms to understand, and now I am ready to teach.
sir, honestly speaking, I remember the maths one course, sir. Combination of you and Vicky sir is very helpful.
Oh, thanks. But not. I moved from maths. Even I am moving with you guys, I guess.
Yes, sir. As we are moving, you are also.
Maybe I am some 3 terms or 4 terms ahead of.
Oh, okay.
So you can. But I won't be moving in the direction of MLT, MLP. Rather, I will be going to statistical computing, linear statistical models in the degree level.
What is the linear approximation of the moment?
What is the
linear approximation of the moment?
Approximation of the
Your movement.
My movement. Yeah. I'm telling that, right? It's not linear approximation. Also, it's like proper fit. So now I am doing MLF. Next, I will be in linear statistical model, statistical computing. So I will be in more in stats kind of machine learning. So I will not be coming into the crude machine learning parts. Rather, I will be giving you this basic understanding. Like I will be teaching you how to construct your home, not the complete home, maybe the basement, like how much deep you should
It's more like
dig.
trending and pattern matching, something like that.
Maybe I will try to I will be there till you get the basement of data science and program, give you the basement of.
That's a good thing.
So, sir, basically that project MLT project is a research paper, or
See, I
So
I'm not
sorry to
sure
interrupt.
about it.
Can we look at the calculation?
Yeah. So maybe we will have this discussion in the maybe in the next
sure,
session.
sir, sure.
Okay.
Okay.
So let me complete this because it's already 10:15. Okay. I should be ending this session pretty shortly. So let me talk a bit about directional derivative. See, why I am discussing all these things is you already have previous terms live sessions, right? There everything is discussed, and this term, what I feel, I felt I'm just giving you some intuitions to how to think about a course. So the same thing I'm doing for stats also, and I'm recommending everyone to go back to the past sessions and look for the contents there. But I will be giving you how to go about the course and how you should be reading the course or contents at least. So that's my prime motive, along with problems, of course. If it is a solve with the session, I can't sit motivating you and to do the stuff. But as I got chance today, I just wanted to take a moment from that. Yes. Okay. Let me talk about this directional derivatives a bit. For this directional derivatives, you should understand what is a partial derivative means first of all. So partial derivative, and in order to understand partial derivative, you should understand what derivative is. So as we saw, derivative is basically the rate of change of function with respect to the variable x, right? So that is the derivative. So if we move to the higher order, just like in this particular case, just if I have any function of second order or r2 to r, if I have any function like this where I have two inputs with one output, something like this, f of x comma y. So now I have two different axes. So one is x axis and another one is y axis. So I have my graph changing with respect to x axis, also with respect to y axis. So my graph will change. So if I vary my x, my function value will change. If I vary y, my function value will change again. And how it is being changed is what partial derivatives is. So partially derivating it. So I'm not completely derivating it. I'm partially derivating it with respect to x or with respect to y. So because I have both x and y, so I wanted to derivate it only with respect to x. That is why it is called as partial derivative with respect to x. So what we do is, so we observe the rate of change of the function f as we keep varying x, keeping y fixed. So I will fix one of the variable fixed and the other variable I will move and see how my function is changing. So that is called partial derivative with respect to x, that is represented it as dou f by dou x of x comma y. The same thing if I do by interchanging variables, it is called dou f by dou y. So the rate of change of f as we vary y, keeping x fixed. So that is called partial derivative with respect to y. So the representations are like this. Sometimes we represent it as f subscript x. Sometimes we directly give it dou f by dou x. So you see the difference. This dou represents, so this represents the partial derivative. Okay. So if I use d, it's represents, usually it represents derivative. Okay. So a quick example I can take of is, if I have f of xy as something like x square plus xy plus y square. So something like this. So if I want to compute dou f by dou x, what I have to do, I have to keep y fixed. So now y acts as a constant now. And y keeping y as constant, I derivate the function with respect to x. So if I derivate the function with respect to x, it will be 2x plus y is constant, so constant times x. So it will be, if I do the derivative, x will go off and constant will remain, which is y. And the constant with respect to y square is a constant as of now because we fixed it. So constant by dx is 0. So dou f by dou x will be 2x plus y. So similarly, if I want to compute dou f by dou y, so when I am computing the partial derivative with respect to y, I keep x constant now. So now x acts as a constant. So constant, if I do the derivative of a constant, it will be 0. And next it will be constant multiplied by y. If I do the derivative, constant will be remain x plus y square derivative is 2y. Like this. So these are the partial derivatives. And as you have heard that we are only seeing the rate of change of f as we vary only one variable. But what if I vary both x and y simultaneously? And I wanted to see how my function is moving in some particular direction. Okay, now if I vary x and y continuously, it will move like region. So think about this. So this is x, this is y. So if I vary x as well as y, my f of xy will no longer move in one direction. It moves like a region. So it will be like some cloud is moving. Okay. So if the cloud will move in x and y, so if you treat like so this is how it will move. So you are seeing from the top, and the cloud is like this. So if you are varying your x and varying your y, that means this cloud will start. So if I am moving x this direction, y this direction, and this cloud will start moving like it will come to this here or here. So that it will move like a region. Okay, so try getting this intuition or use GeoGebra for this. Okay, you will get more intuition. See the graph actually. See, the main problem in mathematics is until two-dimensional, I can put it on the screen. When it goes to three-dimensional and higher dimensional, seeing it in the 3D world will not be possible at all. So you can't see R4 in physical world. You have to be in the mathematical world to observe R4. Okay, so that is why getting intuitions will take some time, but once you get the intuition, all the things will look simpler to you. So try to get intuition through graphs and try to understand how a point is represented in an R4 dimensional, 4-dimensional space, or maybe 10-dimensional space, how the point is represented, how the vector is denoted. Okay, so you can't physically draw a vector in 10-dimensional and see how the vector is, but you can intuitively get some idea of how. See, this is how the 10-dimensional vector looks like, or x1, x2, x10. Okay, so this is a 10-dimensional vector. If I say it is a 10-dimensional vector, if you don't have the intuition behind this, and if you try to bring this particular vector into real world and try to draw, you can't ask me draw me this vector and show me in which direction it is going. So I can't physically draw and show it to you. It's all depends on the intuition. So how you can develop this intuition is start from R1, R2, and without, like, it should be like, once you understand through graphs and once you get the understanding, then dip into the mathematical side of that. So how this is being done, why this is being done. So if this is the case, this is what it is happening. So you should think about all these things, then move to R3, then you can move to Rn, and then you will get the intuition. Oh, acha, if the vector is like this and it has all the positive entries, and if x1 is like this.
So can you just give an example in R3 or R4 so that it becomes
So practice assignment 2, question number 10. It's on the same lines of what ma'am just asked. And I'm not getting the answer.
Okay, I will maybe I will end this session by solving that particular problem. Okay.
Yes, sir, please.
Okay. So let us quickly see this. Okay, let's not go into in deep of R4. At least we are in R2 only, right? So we will have R3 picture. So one is f of xy, and other one is x and one is y. Okay, so treat it like this. So there is a third axis which is the function value. Okay, now I am changing both x and y simultaneously, and I wanted to see the rate of change of f in one direction, in one particular direction, because the rate of change of f will not be same in every direction. So that is what I said, try to get the intuition. So this, from this to this change, and from this to this change is different, or the function, see, okay, so I can't, I told you, I physically it's very impossible. Just open GeoGebra and draw some random function. This function itself, you can take this function itself, x square plus xy plus y square, and put it and see the curve of this. So it will be like a wave, or it will be like some mountain, hill, or something like that. And if you see, if you vary x and y, the rate of change will not be same. For some directions it will drop suddenly, and for some directions it will be like smooth and all.
So,
that
sir,
is
the
why
direction is determined by the magnitude of the vector, or what exactly?
direction is determined.
Like, on what basis did you give this arrows or draw? Is it based on the magnitude or?
No, it's a vector, right? See, this arrow represents a vector.
Yeah, but how steep it should be, or what should be the shape? How is it determined?
See how steep it is and all, it will, then the magnitude comes into the picture, how much is differed, then the norm comes into the picture. So norm actually gives the distance, or distance in the drop. Okay, if there are two vectors, if I wanted to see how far these two vectors are, I have only one possible way, which I can compute the difference between the vectors and take the norm of it. And I can understand, I will say that these two vectors are this much far. Okay, but I'm not worried about as of now the computation part. Rather, I am worried about the rate of change of f will be different in different directions. That is what I want you to understand. So depending upon the direction, the rate of change of that function will change. Okay, it's not that always with partial derivatives itself we can analyze the rate of change of f. Sometimes, not sometimes, there will be one more factor, which is the direction also plays a major role. Okay.
Sir, so x and y are changing by the same amount? I mean, the rate of change of x and y are the same?
No need to be, right? No need to be. See, x can change like some 10 units, y can change like some 20 units by then. So that depends on how fast y varies and how fast x varies. X and y are independent to each other, right? They are free to vary however they want.
Sir, so x is not the independent variable and y is the dependent variable?
No, y is not dependent here. Y is also an input here.
Oh, yeah, sir, yeah.
Okay, so x and y both can vary, and they are independent to each other. It's not that x has moved 10 units and y should also move 10 units. It's not defined, or it's not, we are not worried about like that. So we are only worried that x is changing, y is changing. If x and y are changing, relatively how f is changing. Okay, and this directional derivative, see, this is a derivative of f of x comma y, but why we had directional derivative is because this particular rate of change of f will also depend on the direction in which you are seeing, in which you are worried about. So that particular direction is represented as a vector. So in which direction you want, in this vector direction, in this. Okay, so like that we will compute. So this is also a derivative, but we named it as directional derivative because it depends on the direction also. So for getting the intuition of why direction will also be a factor, I said just go to GeoGebra and start varying x and y's, and you will see the region f of xy how it moves. and it will not be uniform change. For some directions it will not even change, for some directions it will change. So okay, maybe best example I can give you is, suppose you have a disk like this here, and you treat like this disk is being rotated like this, is being varied like this, and it comes to the original position here. So it's like, okay, you treat like it's rotating like this. Okay, now you see this
direction is changing continuously.
You see this particular point, okay, and this particular point. So you pick any 2 points, the rate of change of those 2 points will be different when we change x and y. Okay, so the points in the sense here f of xy values. So that f of xy for 2 different points within the x and y varies, it will be like, it will vary much for one point and it will vary slightly varies for the other point. Or that is what, see, I can't put 3D into 2D screen, so it will get complicated and complicated. That is why take this as an exercise and try it out yourself. Go to GeoGebra and get the better understandings. Okay, if you
Sir,
try it by yourself, you will get it.
so why do we need the higher order approximation actually? I thought for linear regression and all we need the linear approximation, but if
See,
it comes to quadratic approximation,
why do we need is because in order to go for better
okay,
approximation.
better approximation, and is there anything like machine learning related to that?
No, nothing. No machine learning will come into the picture.
Okay, just to approximate the function, that's it.
Sir, we need coding for machine learning?
When you mean by coding, what do you mean by that? Like
Coding
you
in
want to be
Python or whatever. I mean, any kind of coding
for
using
MLF to
programming
no.
language.
For MLF to no.
Okay. The rest maybe, no?
Maybe, yeah.
Okay.
So that is why we had introduction to Python in foundational level.
Yes,
That
yes.
helps for programming people, also for data science people. Okay. So the directional derivative is defined as like this. Del f dot u. So del f is basically, if you take the vector of partial derivatives, is what gradient. So this is called as gradient, and this gradient is nothing but a vector of partial derivatives. So you just put all the partial derivatives in a column vector, that will become your gradient. So it should be transpose. Del f transpose times u. So it's like del f will be, for this particular thing, del f will be del f by del x, del f by del y. It's a column vector, and we have computed the values. It will be 2x plus y and x plus 2y. So this will be the del x plus del y, and u is just the vector. It is given to us, like in which direction you are finding the directional derivative. So if you do the dot product between these two, we are going to get u1 times. So u1 u2 are like, u is like
unit vector or just like vector?
no, this is just a vector.
May or may not be unit.
May or may not be unit. Is it unit? How did professor defined it?
In maths too, it was unit vector.
Yeah. I think it's an unit vector only. It should be unit vector. See, if it is not unit vector, you just have to make it unit vector by dividing it by
No.
norm. Like it's like length of the vector. You just divide it with the length of the vector, you will get unit vector. But okay, yeah, it should be unit vector. Okay. So u is u1 comma u2. So if I do the dot product, I'm going to get u1 del f by del x plus u2 del f by del y. So once this direction is given to you, and once this del f and del f by del x and del f by del y is given to you, you can compute the directional derivative at some point of the function. So directional derivatives also, if you see, it's just the weighted sum of the partial derivatives. So something multiplied by del f by del x plus something multiplied by del f by del y. So that is why it is considered to be weighted sum of partial derivatives. So let me take one example and we will end the session. Maybe I will take the practice assignment example only. Let me open the practice assignment. Question number. What is the question number? If someone. Hello.
I think that person has left the meeting. 10 someone's.
10, huh? Okay. Okay, the directional derivative. Yeah. So let us compute this. So function is given to us, f of x, y, z, which is given to be x square plus 3y plus z square. Z square. And I want the directional derivative at point 1 comma 2 comma 1 and along the unit vector in the direction of 1 comma minus 2 comma 1. So along the unit vector in the direction of 1 comma minus 2 comma 1, is that correct? Yeah. So in the direction of this, I want the directional derivative of this particular function at this point, this. Okay. So if I have to compute that, I need few things. Firstly, I need the unit vector in the direction of this. So what will be the unit vector? So let me represent that as unit vector, and this divided by norm of this. Correct? Am I correct? How do you find
Yes,
the
sir.
unit
Yes,
vector
sir.
in some direction? You just have to divide it by length of that vector. So
length is the norm here, right?
Huh?
Length is the norm.
Length is the norm. So maybe I will write it in ijk, I minus 2j plus k divided by root over. So this is like 1 square plus minus 2 square plus 1 square. So this will be 4 plus 2, 6.
Sir, what does it mean by unit vector is in the direction of 1 minus 2 1? I mean, how do we represent that?
How do we represent that is, see, this is point 1 comma 2 and vector 1 comma 2. Do you know the difference between those two?
No, sir. Can you please explain that?
So where will the 1 comma 2 point be?
That is simple as per the coordinate
As
plane.
per the coordinates.
Yeah, I think the vector part you can.
This will be 1 comma 2. Correct?
Yes, yes.
So this is the point 1 comma 2, which is represented like dot.
Yes.
But vector 1 comma 2, it will start from 0 0 and in the direction of 1 comma 2 there will be a vector till 1 comma 2. So this is vector 1 comma 2. So vector 1 comma 2 is a vector.
So does it start from the origin always?
Yes, from the origin always.
Why? Any particular reason for
That's
that?
how we represent vectors, right?
Okay.
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 So this 1 comma 2 is, if I say vector 1 comma 2, it's like for every 1 unit change in x, there will be 2 units change in y.
Yes.
That's what it means for vector 1 comma 2 means. But point 1 comma 2 is like it's just a single point on the real line. Okay. Now, if you clearly observe, as I said, if I draw this line, all the vectors on this line are scalar multiples to each other. Do you agree? So there will be one more vector which is 2 comma 4 on this particular line, and that also goes in the same direction. Agreed? No?
Yes, sir. Yes, sir.
So even 2 comma 4 and there is 3 comma 6. So if I draw the vector 3 comma 6, it will also go in the same direction in which 1 comma 2 vector is there.
But magnitude is different.
But magnitude is different, that's it. And when I say a unit vector along this direction, what I am saying is I draw a vector in this direction and the length of that vector is 1. So what is the length of the vector 1 comma 2?
So
No?
it's
Root
5.
5, sir.
5.
Length of 1 comma 2 vector.
Root 5.
Root 5.
Root 5. Yes, 1 plus 1 square plus 2 square, which is root 5. So is it at a distance of 1 unit?
No, sir.
No, right? This is root 5 units, right?
Yeah.
So I want a vector which is in the same direction, but the length of the vector should be 1. What can it could be?
Divide the vector by the length. It will be used.
So as I said, it is everything is scalar. All the vectors in this line is scalar multiple to each other. I can I need a vector which is scalar multiple of this. So I say alpha comma 2 alpha, and this vector length should be equal to 1. So if I compute this, the length of this vector, I need some alpha such that the length of, when I say length, this is like alpha square plus 4 alpha square should be equal to 1. So if I solve this, what will I get? Alpha. So this will be alpha times root 5 is equals to 1. Alpha is 1 by root 5. Yes or no? So I want a vector that is in the direction of 1 comma 2. So if it is in the direction of 1 comma 2, I know that that vector is a scalar multiple of that vector, scalar multiple of 1 comma 2. So I simply took alpha times 1 comma 2, which gives me alpha comma 2 alpha. Now this vector, the length of this vector should be equal to 1. So that is what I want, that the unit vector I want. So if I compute the length of this vector, it is alpha square plus 4 alpha square. That should be equal to 1. From there, I can simplify alpha. So from here, it will come to here. So alpha square will come out of the square root and it will become alpha. Root 5 is equals to 1. So alpha will be equal to 1 by root 5. So I will just substitute this here. What I will get? 1 by root 5 comma 2 by root 5. So this is a vector. This is a unit vector in the direction of 1 comma 2. Getting this? 1 comma root 5, that will be somewhere here. Somewhere here. This is 1 by root 5 comma 2 by root 5. And the unit vector is this. And it will also be in the same direction. Getting this or confused?
Get it, sir.
So I was talking to my stats people also. See, our brain will work for only the first 50 minutes. Okay, it can only concentrate on one topic. Okay, after that we will definitely go off from the topic, as it is more than 2.5 hours. I can understand. So that is why just come back, maybe just take break today, have dinner, have some good sleep. Tomorrow morning just come back to the YouTube session and just listen to what all I said till now. It will definitely clear you.
It's a mental fatigue.
Hmm?
It's a mental fatigue, sir. As you rightly said, 50 minutes is the max.
50 is the max. That is why
Yeah.
most of the institutions will have a class for at most 50 minutes.
Oh,
Okay. So this is scientifically proven also.
right.
Okay, so get it done. So first of all, for finding, let me just complete this. So for finding, I need unit vector. I got the unit vector as, if I divide it by norm, I will get the unit vector. So 1 by root 6 comma 2 by root 6, 1 by root 6 is the unit vector along the direction 1 comma minus 2 comma 1. So I got u, and then I need to get del f transpose. So
Sir, unit vector is having a magnitude of 1, right?
yes.
And one magnitude 1 in the sense, or like exactly 1, or in terms of the other vectors?
No, exactly 1.
How is that? Or can you
See,
just
this is
show?
the vector.
Okay.
If you compute the magnitude of this vector, you will be getting 1.
Okay.
Okay, and
Okay.
also it will be in the direction of 1 comma 2 only.
Okay.
So u we got it as 1 comma 1 by 6 minus 2, sorry, root 6, and 1 by root 6, and I have to find del f. So del f is again del f by del x, del f by del y, del f by del z. Okay, so individually we can compute del f by del x. So we have given the function del f by del x is 2x, del f by del y is 3, del f by del z is 2z. So this will be 2x, 3, 2z. Okay, now we want the directional derivative at point 1 comma 2 comma 1. Now x naught, y naught, z naught is given to us as 1 comma 2 comma 1. So that means x is 1, y is 2, and z is 1 again. So 2 times 1, it will be 2.
Sir,
So
is there
del f.
any? Sorry. Okay. Sir, is there any relationship between derivatives, vectors, and all? It is
Derivatives, vectors, and all, yeah.
like basically derivatives and vectors. Like what? How could we establish a relationship between them?
See, gradient is the establishment, right? See, gradient is a vector, and it takes all the partial derivatives.
Okay.
So whatever you see inside this are partial derivatives.
Okay.
And
So
collection of all those partial derivatives will become a vector. And that is what we call it as gradient of a function.
Sir,
Okay.
so what is the intuition when we say find gradient at a particular point, sir? So for example, gradient at 1 comma 2 comma 1 is 2 3 2 comma 3 comma 2.
Mm-hmm.
So how to understand it?
So the rate with respect to x is 2, the rate with respect to y is 3, the rate with respect to z is 2 at the point 1 comma 2 comma 1. Okay, the rate of change of f with respect to x alone is 2, with respect to y alone is 3, with respect to z alone is 2. So
Around the
collectively we
point.
are seeing
Around 1 comma 2. Okay.
at that point.
But at one point the function value is fixed, sir.
But we are not looking at the function value, right? We are looking at, oh, see, when I say derivative, it's like just side of that point. So when I say at 1 comma 2 comma 1, it doesn't mean that you are seeing it at that particular point. Usually we say at, because see, these derivatives are very small terms, okay, small distances. So it's like when I say 1 comma 2 comma 1, you should always think in the interval of 1 minus h comma 1 plus h, 2 minus h comma 2 plus h, 1 minus h comma 1 plus h. So in this interval you should always see partial derivatives, everything. See, that is why we call it as calculus, okay. Calculus is like, in biology, if I talk it in the biology terms, if you see the DNA of, how can you see the DNA? Can you see with naked eye?
No, sir.
No. So you need microscope, right? So
Yes, sir.
if you have proper microscope, then only you can see the DNA, or you can see the distance between two cells inside your body. So you should think in that way. So whenever we say derivative, we talk about derivative. It is always like, it is not exactly at that point. It is always like something around that point, some small interval, very small interval, which is not even visible. Okay, so that's how you should
So in
think.
that small interval, the rate of change with respect to each variable.
Each variable is 2, 3, and 2.
Yeah, it depends upon the functions, right?
Yes.
Like
Yes.
the given function.
Yes.
So here it's the y is linear, so anyway its derivative will be a constant only.
Correct. So when I look at this function, you see this function, when I fix x square and z square, and if I wanted to see the rate of change of this function when I change y, so if you change y, the function value will change by 3 times of y. That's it. So if you are fixing x square and z square constant, it will change, like if you are changing y by 3 units, your function will change by 9 units, 3 times of that. So it's like always the rate of change will be 3. So it will not depend on y.
So
that's
in
why it
that
is
small
constant.
interval, sir.
Again, in that in that small interval, and throughout also it is not depending upon y. You see, this 3 is not depending on y. So if you consider it at any point, this is going to be 3.
Okay.
Okay. So you have del f with you, you have u with you. Just do the dot product, you will get the answer. So it's like 1 by root 6 into 2 plus 2 minus 2 by root 6 into 3 plus 1 by root 6 into 2. So this will be the directional derivative del f. So there will be lots of things at 1 comma 2 comma 1 in the direction of 1 comma minus 2 comma 1. So this is the value. If you simplify this, you will get some value. That will be the that will be the answer. Okay.
Yes, sir. Thank you for this class.
Thanks, and we will have a good day. We will meet in the next class. Yeah.
Thank you,
Thank you,
sir.
sir. Thank you very much.
Yeah.
Thank you,
Bye.
sir.
Bye.
Thank you, sir.
Thank you,
Thank
sir.
you, sir.
Thank you, sir. Good night.
Yeah. Good night.
Thank you, sir.